Since the earliest days of flight, designers have tried to make more efficient aircraft by removing the components that don't produce lift, such as the tail and the fuselage. The task, though, is deceptively simple, and in fact, it's quite complex because as you remove these devices from the wing has to do all the work of stability and control, what the Wright brothers called balance and steering. The wing has to be controllable in yaw, pitch, and roll. And probably the most successful designer of all-wing aircraft was Rymar Horton. And we have an aircraft at the National Air and Space Museum that exemplifies his all-wing design, and that's the Horton HO6 V2. Now, what Rymar did was he used a high aspect ratio structure, the smoothest possible with the construction materials he had, which were primarily wood and metal. He also used a semi-prone cockpit layout, similar to how a motorcycle rider sits on his or her motorcycle in a low tuck position. And all these techniques Rymar Horton used to eliminate the drag and make the aircraft, again, a high-performance sport sailplane, have the greatest performance possible. And up until the 1950s, when electronic controls were introduced on aircraft to stabilize and control all-wing airplanes, Rymar Horton was probably the most successful designer of all-wing aircraft.
We need more than aerodynamics to keep an airplane in the air. As Samuel Langley found out at the dawn of aviation, stable and controllable flight are also critical. Samuel Pierpont Langley, Secretary of the Smithsonian Institution in the late 1800s, was convinced that powered flight was possible, despite public perception at the time. Langley set out to build up a technology program to build a successful powered aircraft. He built a series of aerodromes, as he called them. These were subscale model aircraft that were designed to be a practical demonstration of the principles of flight. After several years of applied research and development, Langley's team converged on a design that they thought could sustain powered flight. The Aerodrome 5, weighing in at 24.3 pounds, had a tandem wing configuration based on a cambered airfoil. The aircraft was driven by a 1-horsepower steam engine, powering twin propellers located midway between the front and rear wings. Langley was fixated on ensuring that the aircraft would be able to sustain stable flight. One of the stability features that he designed into his wing was a strong dihedral angle of 15 degrees. This is the upward deflected angle of each wing. This design feature is incorporated in order to counteract disturbances in the roll of the aircraft. If a gust or some other disturbance causes one of the wings to dip downward, that wing then becomes oriented more parallel to the oncoming flow, and its lift goes up. At the same time, the opposite side wing has less lift. This imbalance of lift creates a restoring action that naturally returns the aircraft to its stable, upright condition. In addition to wing dihedral, Langley also incorporated a cruciform tail. This is the same basic idea as what is seen on arrows, and had been proposed by George Cayley many years before. With stability features in place, wing dihedral and a tail, but no control surfaces, Langley oversaw the first flight of Aerodrome 5. The flight took place on May 6, 1896, over the Potomac River, near Quantico, Virginia. Langley's crew launched the aircraft from the top of a houseboat floating in the river, commencing a 1.5-minute flight that covered almost half a mile. Langley then trumpeted the news around the world. He had achieved the first sustained engine-powered flight of a heavier-than-air aircraft. What Langley had neglected was control. The aerodrome lacked suitable provision for steering the aircraft in the desired direction of flight. There wasn't even a pilot on board, and the aircraft merely landed in water. In contrast to Langley, the Wright brothers paid much more attention to aircraft control. they understood that control, as well as stability, were essential to sustained flight. The Wright brothers' key insight was in how to achieve roll control. Their idea revolved around differential control of the angle of attack of each wing. If the left wing could be set at a lower angle of attack while the right wing is set at a higher angle of attack, then the left wing's lift would decrease and the right wing's lift would increase. This imbalance in lift would cause the aircraft to bank to the left. Once they had developed this concept, the difficulty was in how to achieve this differential angle of attack in practice. A flash of inspiration occurred to Wilbur Wright one day while he was working in their bicycle shop. While talking with a customer, Wilbur found himself mindlessly playing with an empty cardboard box for a bicycle inner tube. Playing with the four corners of the box, he twisted it back and forth and was suddenly struck with the idea that this warping technique could be used to produce the differential angle of attack that they needed for roll control. This insight led to their development of the wing warping technique, which they used for roll control on all of their early aircraft, including the 1903 Wright Flyer. They recognized that this method of control was a unique contribution to aviation, leading to the filing of a patent application to protect the idea. Since roll control was so fundamental to successful flight, the Wright brothers' patent claim was essentially an attempt to assert priority claim over all aircraft designs. This assertion led to incredibly contentious disputes between the Wright brothers and their contemporaries. Stability and control have been critical aspects of aircraft design and piloting ever since. A great place to start any analysis of stability is with the definition of a coordinate system for the aircraft and the rotations about those axes. The longitudinal axis is one that runs along the length of the aircraft's fuselage, and roll of the airplane is a rotation about the longitudinal axis, where the wingtips move up or down. This is the aspect of aircraft control that Langley ignored, but that the Wright brothers ingeniously solved. The next axis is lateral, which runs along the span of the wing. The aircraft pitches about the lateral axis, pointing the nose of the aircraft up or down. The third axis is the directional axis, or vertical axis, which projects vertically out of the fuselage. The aircraft yaws to the left or to the right about the directional axis, pointing its nose towards different azimuthal locations. This coordinate system is called the aircraft body axis system, since it is fixed to the aircraft. The origin of the body axis coordinate system is centered on the aircraft's center of gravity, which I'll refer to as the CG. The center of gravity is like a centroid, a center point for all of the mass of the aircraft. If the aircraft acts as a solid body, all of the rotations take place around the center of gravity. The placement of an aircraft's center of gravity is critical for all aspects of stability and control, as we'll see shortly. One tangible example of this is how the aircraft is loaded on the ground. The Boeing 727, for example, is a tail-heavy configuration in its empty configuration, due to the placement of all three engines at the rear, far behind the main landing gear. There have been a few instances where the ground crew has begun loading an empty 727 from the rear, adding further mass behind the main landing gear. The additional mass at the rear of the airplane can shift the center of gravity far enough aft that it moves behind the main landing gear. The result of this is a very undignified tilting of the aircraft back, such that it rests on its tail. So we have three axes and three rotations: lateral, longitudinal, and directional axes with their corresponding roll, pitch, and yaw rotations. We'll discuss how to maintain stable flight of the aircraft with respect to these axes. In other words, keeping the aircraft pointed in the desired direction of flight. The other aspect of the problem is aircraft control, which is manipulating rotations about these axes in a desired manner. Now, what exactly produces rotations about the body axes? The source that induces a rotation is termed a moment. It's easiest to think of a moment as an applied torque. For an example, unscrewing the cap on a jar. It takes an applied moment to twist the cap off. A force acting perpendicular to a line passing through the center of gravity will produce a moment about that center of gravity. This is a critical concept for Newtonian mechanics and is fundamental to aircraft stability and control. Just like we could write Newton's second law to relate an applied force and a resulting linear translation, we can apply Newton's second law for rotational motion. An applied moment will result in an angular motion. An aircraft that is in steady, straight and level flight is in a trimmed condition. By this, we mean that all of the forces and all of the moments acting on the aircraft are in equilibrium. There is no net force and no net moment, such that the aircraft will experience no translation or rotation. Let's now focus on the concept of stability. The main idea is that a stable design will return to its initial equilibrium condition, if perturbed, by a wind gust, for example. A neutrally stable design will change from one equilibrium state to another state when subjected to some change. And a perturbation to an unstable design will cause the system to diverge from the equilibrium condition. The perturbation would grow until the aircraft completely flips over. It's also important to recognize that there are degrees of stability. A very stable aircraft will more readily return to its equilibrium condition, even when subjected to a very strong perturbation. However, the trade-off for high stability is that maneuverability is suppressed. For this reason, many aircraft designers aim for a stable aircraft, but without too much stability. Fighter aircraft in particular must be as maneuverable as possible. Thus, fighters are often designed to be inherently unstable, but use active control systems to maintain flight. An example of an unstable system is my attempt to balance a long, slender rod in the palm of my hand. Any small perturbation due to a breeze in the room or the tilt of my hand will lead to the rod falling over. The instability results from the center of gravity of the rod being so high above my hand. The higher that CG is, the more unstable the rod is. However, I can attempt to maintain balance by actively moving my hand to support the rod. If I sense that the rod is tilting to the left, I'll move my hand in that direction in order to keep it upright. In the same way, an aircraft's closed-loop control system can overcome an inherently unstable design by continually adjusting the aircraft configuration to maintain flight. So clearly, we see that the center of gravity is critical for aircraft stability. The other critical feature is where the net forces and moments act on the aircraft. The net force is a very useful representation when thinking about aircraft stability. Even though the pressure is acting across the wing, we can integrate or sum up the net contribution of the entire pressure distribution to represent the same effect by a single force vector acting at a point on the aircraft. We call this net force on the wing the center of pressure. The location of the center of pressure relative to the center of gravity will determine what rotational motion happens. If the center of pressure is co-located with the center of gravity, then no rotations will occur. However, if there is some distance between the center of pressure and the center of gravity, then the net force vector will produce a moment about the center of gravity. For a given magnitude of force, a larger distance between the force and the center of gravity will produce a stronger moment. That is the same idea, by the way, as using a cheater bar to break a tight lug nut on your car. A long cheater bar with the same amount of applied force will produce a stronger torque or moment to break the nut free. Let's now take a look at how the relationship between the center of pressure and the center of gravity can affect the moment on an airfoil in a wind tunnel. For thin airfoils, it turns out that the center of pressure will be at the quarter chord position, 25% away from the leading edge to the trailing edge. So we'll assume that the net force acts at that point on our airfoil. I'm going to test several airfoil models in the wind tunnel, where the mounting location or pivot point is set at 3 different locations: at the leading edge, at 25% chord, and at 50% chord. The mounting location will emulate the CG location on a free-flying wing, since I'm constraining the rotations to occur about the mounting point. Let's first try out the leading edge mount. Here, the net force acts at a point behind the pivot point. If I give the airfoil a perturbation, it's going to return to the equilibrium condition. This is going to be an example of a stable configuration. So you can see when I perturb the airfoil, it returns right back to its equilibrium condition. The perturbation causes the airfoil to pitch up, which results in an increase in the lift due to the linear relationship between lift and angle of attack. Since the location of the center of pressure, or net lift, is located behind the pivot point, it produces a restoring moment that reduces the angle of attack back to its equilibrium condition. Now let's turn our attention to the airfoil with the pivot point located at the quarter chord. In this case, the center of pressure is co-located with the center of rotation. So when I turn the wind tunnel on, the airfoil is going to oscillate in the wind since the pivot point is very close to the center of rotation. So the center of rotation is the same as the center of gravity, and it's the same as the center of pressure. This exemplifies neutral stability. If an aircraft were made like this, it would be more maneuverable than the earlier stable condition, since it doesn't require a very strong perturbation to change its operating condition. And then finally, we're going to take a look at the aft-mounted pivot point, where the rotations occur about 50% chord. Before I conduct this experiment, let's think about what we expect to happen. Now, the net lift force is acting at a point ahead of the pivot point. If a perturbation causes an increase in the angle of attack, then the airfoil is going to generate more lift. This part so far is the same as the previous two cases. However, the line of action of that net force is ahead of the pivot point, causing a rotation in the opposite direction from what we saw with the leading edge mounted airfoil. This applied moment will cause the angle of attack to increase, which will further increase the lift. So you can see now that this represents a runaway condition that will be unstable. So you see what happens when I turn the wind tunnel on and let go. Wow, it just pitches way up to the vertical direction. The position of the center of gravity relative to that center of pressure dictates this unstable condition. So let's summarize these key concepts. For stable flight, an aircraft must have a center of pressure that will induce a moment about the center of gravity that restores the aircraft to its equilibrium condition. Since an increase in angle of attack corresponds to an increase of lift, the center of pressure must be behind the center of gravity. All stable aircraft are configured this way. However, this raises an issue. If the wing's center of pressure is behind the center of gravity for purposes of stability, how can we keep the aircraft from nosing over during a routine flight? It seems that the aft position of the center of pressure would produce a nose-down pitching moment, unless we do something to balance things out. Further compounding this problem is the fact that most airfoils have a characteristic nose-down pitching moment when they are producing lift. The net effect of these two factors is a strong nose-down tendency that somehow must be balanced out. The answer to that balancing problem is in the horizontal tail. The tail is used to trim out the forces and moments, to bring everything in balance. In order to trim the aircraft, the tail must actually produce a downforce on the rear of the aircraft. The downforce is set to produce a moment that counteracts the moment resulting from the gap between the center of gravity and the center of pressure. Since the horizontal tail must produce downforce, it is typically configured with a negative incidence angle. The example you see here has an angle of roughly 4 degrees. The larger the gap is between the center of gravity and the center of pressure, the more stable the aircraft will be. but also more downforce from the tail will be required. Now, the downforce produced by the tail actually works against the overall goal of lift production. Thus, the wing must work a little bit harder to produce even more lift to overcome the downforce needed by the tail to balance everything out. With the extra lift production of the wing, there is extra induced drag, so there is some inefficiency to this arrangement. Also, the presence of the tail adds parasitic drag due to skin friction, and a small amount of induced drag due to production of the downforce. So it's not an ideal solution, but it is by far the most widely implemented method for trimming out an aircraft in flight. Another less common approach involves placing the horizontal stabilizing surface near the front of the aircraft. This configuration is termed a canard, which has been seen on aircraft ranging from the Wright Flyer to the XB-70. We'll discuss the trade-offs involved with canards in a few minutes. So now we see how critical the center of gravity is to the stability of an aircraft. In fact, it's so critical that each aircraft has clearly defined limits for loading in order to keep the aircraft stable. On many aircraft, it's quite possible to load up the airplane with heavy cargo in the back such that the center of gravity moves too far aft and the aircraft becomes unstable in pitch. This is true for nearly all aircraft, not just the Boeing 727. Smaller aircraft are particularly susceptible to this challenge. As a pilot, I carefully calculate the position of the center of gravity before every flight that I take, and I pay particular attention to this when I have adult passengers sitting in the back seats or any luggage in the aft cargo hold. Calculation of the center of gravity involves determining the weight of each person or bag on the airplane along with its location. A lightweight bag placed in the rear cargo bin can have as much impact on the CG as a heavier bag that is in the middle of the cabin. The product of the weight and the distance from a reference point is the moment, and the sum of all the moments about the center of gravity must be within limits set by stability. Location of the center of gravity is a concern even on commercial flights, affecting the placement of cargo or even passengers. Maybe you've experienced this before, where the flight attendant may ask a few passengers to move to a different part of the airplane due to weight and balance reasons. It's true, the flight attendant is not out to simply inconvenience you. It really does matter that the aircraft stay within the appropriate limits for center of gravity. So it really is a good idea to comply with those directives. Tragically, weight and balance was the likely cause behind an incident at Bagram Airfield, Afghanistan in 2013. Shortly after takeoff, a freight-carrying 747 operated by National Airlines crashed in a large fireball that happened to be captured by a driver's dash cam. Takeoffs from the Bagram Airfield are already challenging due to the typical aggressive climb-out maneuver for avoiding enemy fire and the nearly mile-high elevation of the airport, which decreases an aircraft's performance. The 747 appears to be pitched nose-high to an excessive angle of attack, leading to asymmetric stall of the wings, nose over, and then crash. The initial nose-up was found to be caused by a rearward shift in the plane's military cargo, which had not been properly secured. As the weight shifted rearward, the center of gravity moved aft of the center of pressure, causing the lift and angle of attack to increase up to the point of stall. This tragic incident highlights the critical nature of the center of gravity on aircraft. Now, let's turn our attention to the other two coordinate axes. So far, we've been focused on pitch stability about the lateral axis. The longitudinal and directional axes must also have inherent stability for safe flight. Stability about the directional axis is accomplished through the use of a vertical tail. Unlike the horizontal tail, however, the vertical tail is mounted with no incidence angle. If the aircraft yaws to one side or the other, or if the wind shifts direction, the vertical tail will then be at an angle of attack, such that it produces a side force, which creates a restoring moment. Thus, the vertical tail is effective in either direction, and for this reason, it's usually constructed from a symmetric airfoil. Roll stability about the longitudinal axis is achieved through the use of dihedral, which we briefly discussed earlier in our description of Langley's aerodrome aircraft. When the wing is set at positive dihedral angle and the aircraft dips a wing, that wing will produce more lift, which creates a restoring moment to bring the aircraft back to a wings level condition. Okay, it's now time to shift our focus from the all-important topic of aircraft stability to the related topic of how control of the aircraft can actually be achieved. Let's start by recalling that one of the key differentiators between Langley's attempts at flight and the Wright brothers was successful control of the aircraft. The Wrights developed an ingenious system for warping the wings in order to achieve differential angle of attack on the two wingtips for roll control. However, we don't see the Wright brothers' concept on aircraft today. What developments have happened since then? Well, in the early days of flight, Glenn Curtiss was a contemporary and chief competitor with the Wrights. In his effort to avoid licensing or infringing upon the Wrights' wing warping patent, he developed roll control using ailerons instead. Ailerons are small flaps located at each wingtip, which provide the same result as wing warping, but through a much more practical manner for modern aircraft. As it turns out, since it's easier to deflect a small control surface on the wing than to twist a large metal wing. When a pilot wishes to bank the aircraft to the right wing's aileron is deflected upward, while the left wing's aileron is deflected downward. The deflection of the aileron serves to locally increase or decrease the camber of the wing, thus changing its local lift production. Differential deflection of the ailerons then produces increased lift on one wing and decreased lift on the opposite wing, leading to a rolling moment. The ailerons are almost always mounted at the wing tips in order to increase the length of the moment arm available for maximizing the rolling moment for a given amount of deflection. Pitch control about the lateral axis is achieved through deflection of elevators, typically mounted on the aft end of the horizontal tail. The elevators act in the same way as ailerons, except their size is typically larger, and the elevators move in unison to pitch the aircraft nose up or down. Yaw control about the directional axis is achieved through deflection of a rudder on the vertical tail. The rudder essentially acts as a flap on the vertical tail, producing side force in one direction or the other to steer the nose of the aircraft. The primary factor that dictates the size of the vertical tail and its rudder on commercial aircraft is actually seldom encountered in flight. Most commercial aircraft have more than one engine for the purposes of redundancy and safety of flight. The engines are sized such that the aircraft could completely lose the operation of one engine and still have enough thrust available to safely climb out from an airport, although with greatly degraded performance. However, if an aircraft unexpectedly loses an engine, then the pilot has to work hard in order to maintain control of the aircraft. This is because the asymmetry in thrust now produces a significant yawing moment on the aircraft about the directional axis. One engine will be producing maximum thrust in order to keep the aircraft aloft, while the non-functioning engine will be producing extra drag as it windmills. This coupling of strong thrust on one side and extra drag on the other causes a very large yawing moment. The pilot must overcome this adverse yawing moment through the application of full rudder to push the nose against the adverse yaw. The most critical condition for losing thrust from an engine is during the takeoff roll, just after the point where the pilot has committed to the takeoff. At this condition, the velocity will be relatively low, which reduces the amount of dynamic pressure available for the vertical tail to produce sufficient side force. The other key limiting factors are the altitude of the flight and the temperature at the time that the flight occurs. A high-altitude airport on a hot day will have low density, which also reduces the amount of dynamic pressure or the amount of airflow available for side force production. Thus, these conditions of low speed, high altitude, and hot temperature will dictate the required size of the vertical tail and rudder. Under these extreme conditions, the vertical tail must still be able to generate enough side force, which, acting through a moment arm to the center of gravity, will produce a balancing moment to overcome the uncommanded yaw. So we see that a very rare condition indeed actually dictates a substantial design feature. If it were not for the rare but critical situation of a lost engine, the vertical tail on a multi-engine aircraft would be much smaller. What if we could find another way to maintain trimmed and stable flight without the use of a horizontal tail and elevators? Let's conclude by considering a few alternative concepts. What are some other innovative concepts that are out there flying today? Although ailerons displaced the wing warping technology of the Wright brothers for almost a century, NASA and other designers have been exploring new variants known as wing morphing. Instead of exposed flaps and hinges, the idea in these new approaches is to bring flexibility inside the wing, which promises to lower drag and bring greater fuel efficiency and even reduce noise at airports. Or there's the concept of a canard, which is seen on a variety of aircraft ranging from turboprop business aircraft such as the Beech Starship or the Piaggio Avanti, to supersonic aircraft such as the Tupolev Tu-144, Saab Gripen, or the North American Aviation XB-70. A canard is also found on experimental aircraft such as the tailless Boeing X-36. We saw a few minutes ago that the horizontal tail produces downforce, which the wing must overcome through the production of extra lift. The reason that the horizontal tail produces a downforce is because it's located aft of the center of gravity. But what if we moved the horizontal stabilizing surface forward to a point ahead of the center of gravity? Then we would need to provide an upward-oriented force in order to achieve the necessary balancing moment. This is the entire idea behind the canard. However, there are a number of nuanced challenges that limit the widespread implementation of canards instead of horizontal tails. Some of these issues include interactional aerodynamics between the canard and the main wing, as well as poor stall characteristics if the main wing stalls first. The other key departure from the traditional aircraft configuration is the flying wing. This type of aircraft has been most commonly produced by Northrop Grumman, exemplified by the B-2 bomber, but otherwise is not widely used. Boeing has considered a variation on the flying wing for their blended wing-body aircraft, which is a significant change from the conventional tube and wing configuration. The advantages of a flying wing are improved stealth capabilities due to the lack of radar reflections from the tail surfaces and the opportunity for more efficient flight due to minimizing or eliminating the tail area. But how can stable flight in a flying wing be achieved? The trick is in how the balancing moments for the aircraft trim are created. The flying wing can be designed with a reflexed trailing edge, which ends up producing a net positive pitching moment, which can be used to counteract the nose-down moment produced by the center of pressure being behind the center of gravity. Or another stabilization technique involves sweeping the flying wing backward and tailoring the span-wise distribution of lift such that negative lift is produced near the tips. These effects also change the net moment acting about the center of gravity and still produces a trim condition. Pitch control is accomplished in the same way as with traditional elevators, and directional control is done in a unique way since there is no vertical tail or rudder on a flying wing. Instead, yaw control is achieved through differential deflection of control surfaces on either wing, which act like spoilers and produce more drag on one wing or the other, which induces a yawing moment. However we achieve it, stability of the airplane is all about producing forces and moments that restore the aircraft back to an equilibrium condition when perturbed. Appropriate tail surfaces, or forward surfaces, are typically used to trim the aircraft under steady flight conditions. Meanwhile, control of the aircraft typically involves deflection of control surfaces to alter the pitch, roll, or yaw moments acting on the aircraft's center of gravity. This has been the typical arc of technology development. But the most recent aircraft designs are allowed to be inherently unstable for enhanced maneuverability, while they are stabilized through digital feedback systems. Stability and control are essential, but how we achieve them may look very different in the future.